Okay, Assalamu alaikum. Good evening, ladies and gentlemen, and good morning on the west coast of the US. Tonight, we are privileged to have Dr. Majid Abdelsamie. Dr. Majid Abdelsamie, I'll just give the brief introduction. He is right now postdoc at the Lawrence Berkeley National Laboratory. His expertise are in the field of fabrication and characterization of functional materials used for the solar cell applications. Majid obtained his BSc in Metallurgical and Material Engineering from Swiss University, Egypt, and he did his PhD in, at the coast. And after that, he did postdoc at the Stanford Linear Acceleration Laboratory. And then currently he's still postdoc at Lawrence Berkeley National Laboratory. Tonight, he's going to talk about organic hybrid solar cells from in situ diagnostics towards scalable fabrications. The format will be, I will mute everyone and Dr. Majid will unmute himself. And if you have any question in between, you can raise your hand or you can write your question in Q&A tab. We'll take the question at the end, by the way. Dr. Majid, over to you. You can take the mic, please.
Thank you for the introduction. So as Dr. Sadiq said, I will be talking today about organic and hybrid solar cell materials. I use in situ characterization techniques to understand the formation of the active layer of the solar cells, and then I try to use this in order to get some guidelines for scalable fabrication. So this is outline of the talk today. So first I will
interrupt Dr. Majid. I need to mute all. You can unmute yourself.
Okay.
Please go ahead.
So the outline of the lecture today will be, I will do some introduction about solar cells in general, then I will introduce the methodology that I'm using in the research, and then I will talk in two topics. First one is the organic photovoltaic. This work PhD at KAUST, and then I will go to hybrid organic inorganic materials. Usually it's Perovskite materials for solar cell applications, and this was mainly the work done during my postdoc positions. Then I will end up with current and future research directions. Yeah, for the motivation for the work, as we have seen, so there is energy demand in the world that is increasing every year, and the solar energy itself has a large share of the energy that comes to the Earth, but it is not yet used. And due to the energy demand on the right that is increasing over time, we need to increase our efforts into the renewable energy. And as we see, the expectation to have a larger share over time. So currently here we have a small share in the renewable energy market, but it's expected to increase. So that's why we need to do more research in this area in order to meet this demand. There are different generations of solar cells. The first generation is based on silicon solar cells, either monocrystalline or polycrystalline, and also multi-junction solar cells. But this generation, it was very expensive because it requires very high temperature to process the silicon. So that's why people has invented the second generation, which relies on thin film solar cells, and it was using amorphous silicon, cadmium telluride, or SiGs. But I think each of these had some drawbacks. Like the amorphous silicon was having lower efficiency than the crystalline silicon, and also the other two, they have problems like toxicity of some of the materials, and also has problems with the rare. Some of the materials are rare, like the beryllium is rare, and also indium is rare, and making their cost is very expensive. So the research community has moved to a third generation, which tries to solve the issues of the second generation and tries to avoid using toxic or rare materials, and also to lower the cost of the fabrication. And this includes many types, but I'm just including here three of them, which is organic solar cells, and perovskite solar cells, which is usually hybrid organic inorganic material, and also quantum dot solar cells. And there are also other types of third generation solar cells. Or why we organic in general, organic or perovskite solar cells? So these two classes of material, they can be processed by solutions. So they can be done on roll-to-roll processing. As you can see here, they can be printed as we print on paper. And also they can be flexible, so they can be applied to anything. They can be applied to bags or into windows. It can be applied into large areas also on the building by being having some transparency. And they have a low cost and low energy payback time. And they can have a very cost-effective manufacturing, so we can make them in very large areas with low cost. So the methodology that I have been using in these classes of materials. Firstly, we start by a precursor material for solution processing. Usually, this is a solution material. We mix different compounds in solution, and then we use different processing techniques to reach to the final product. And most of the research are done on the final product. We will try to characterize the final film, how it looks like, what is the properties of it, and some people also they try to do precursor material, try to understand what was the initial state. But most of the research are done on initial state or final state, and less research are done on the in situ, how this happens during time, how we transfer from the precursor material to the final product. So what I'm trying to do is to employ some technique, some in situ techniques to see how the material is it changing from initial state into the final state, and try to watch this on real time. And the main goal of this is to establish the relationship between the processing, so the processing conditions that we use, and the structure in the final state, and also the properties of the final state, and also try to apply these into the function. And the main thing that I try to do is to do in situ characterization techniques. And this is very challenging because most of these, they are not available. You cannot just purchase them. So you need to build the technique by itself. And the technique will vary from different processing strategies. So you need to build a unique tool in order to do this. It's not something that is usually available. So I employ in situ techniques that I usually build to match the specific processing, and then I try to understand the mechanism of the film formation, how this happens, how we reach from initial state to final state, what is the action pathway during this process. And I try to get from these some guidelines in order to control the final properties and the microstructure of the final product. And then I try to use this to improve the performance of the material, or to understand why a specific processing technique is good for the function and for the efficiency. And I try to use this also to do scaling up of the process, because some of the material processing techniques can be applied in labs, but can't be applied in large production. So I try to compare different techniques that can be applied in lab and techniques that can be applied also in large production, in order to find some scaling up of the fabrication. We go back to the outline. So now I will talk about the first topic, organic photovoltaics. I will have a brief introduction into the organic photovoltaics, and then I will move into the research. So for organic photovoltaics, so it uses organic semiconductors. So usually for solar cells, we have like a p-type material and n-type material, and we shine some light, and this light is absorbed by the material, and the absorption leads to the formation of electron and holes. And the goal of solar cell is to try to extract electron and holes at the electrodes. So we need first to separate these electrons and holes. So for organic materials, organic semiconductors in general, they have a high binding energy, which means when they absorb light, they form what is called exciton. So the exciton, it's if you see here, it's electron and hole, but they are bound. They have a very strong binding energy between electron and hole, and they are bound together. So this makes it difficult to separate them. So to separate them, they need to diffuse into an interface of p-type material and n-type material, and then at the interface they can phase separate. One the electron will go to the n-type material, and the hole will go to the p-type material. So the main thing that happens, we have a light absorption, and then the excitons, after forming, they have to diffuse to the interface, and then they dissociate at the interface, and after dissociation, they have to move to the devices. Also, the organic semiconductors has other limitation, which is a diffusion length. So the charges can't move large distance before they recombine. So the excisions might recombine very early. So if we use a bilayer, like a donor and acceptor on top of each other, we will not be able to have efficient solar cells, because also we have a low interfacial area. The area between the donor and acceptor is small. It is just this interface. So the research community has invented what's called bulk heterojunction, which is a blend of donor acceptor material in the nanoscale. So the donor material and acceptor material, they have nanoscale morphology, and this nanoscale morphology helps to the charges to move to the respective electrodes. But the structure of this nanoscale morphology is very important for the final product. So this is kind of like how it looks like, the morphology. So we use a donor material and acceptor material. Here the black is the acceptor material, and the blue, the red is the donor material. For this we have three-phase domains. So we have the pure donor and pure acceptor, and we have interface between them. And so because of this complexity, we need to have a specific domain size and a specific domain duality in order to have a good efficiency solar cells. For example, if we have very large domains, then we have low interfacial area, and the interfacial area, it is the place where the charges are generated. So we might have low efficiency. Also, if we have very small domains, the charges will not be able to reach the electrodes. They can be trapped into the smaller domains. So we need to have a specific domain size, and also we need to have a specific domain purity. If we have impurities inside a specific domain, we are creating traps, and these traps will also affect the efficiency. So we need to control this morphology by using some processing techniques. And usually people use a specific solvent. The choice of the solvent will affect how this morphology look like. So we can see here, if we use different solvents, we can get different phase separation between donor and acceptor material. And also, if we use different additives, we can use different additives to manipulate this. For some of the additives can increase that phase separation or can reduce it. Like in the one in the left, we don't have donor acceptor domain are mixed. So when we use additives, we induce separation. They start to separate into different domains. For another case, when we cast without additives, we have very large domains, but this is bad for solar cells. So we need to use some additives to make the domains smaller. And also we can use some annealing treatment in order to induce these kind of changes. So we can use different processing strategies to control the microstructure. And so what I'm trying to do is to do in situ characterization in order to understand this process. So the first topic that I have done during my research is to make a new technique that can probe the film formation in situ. So I have implemented, I have made a new device that can help us to do in situ UV absorption during spin coating. So spin coating, if someone doesn't know what is spin coating, so we start by solution, and we have the solution. As you can see here in this picture, we add the solution into our substrate, and then we have a motor to spin this substrate at high speed to form a final film. So what I tried to do, so I made a new technique that can help us to watch the changes on the film during the spin coating. So we start by initial set by, like, for example, by a polymer material or small molecule material. That is, it's kind of dispersed in a solution, and then we spin coat to form a film. And this technique can help us to see this transformation from the solution to solid state. And as we can see here on the right, I'm trying to probe the absorption at different wavelengths. So these colors correspond to these colors. So we can see the absorption. This is amorphous. This is the solution peak, and the red and blue are the peak of the crystalline film. So we can see here, we can watch the whole process. We can watch from solution as the solution is leaving the film, and we can see also the final steps. And we have here 3 steps. So during spin coating, initially we eject a lot amount of solution at the beginning, and then we get evaporation of the solvent, and finally we can see the solid state formation. Here the material starts to crystallize and form the final product. And the way we do spin coating can affect this process, like how much time is needed for this to happen. It will affect the final product, as we will see now. So this is the first example. So I started by just one material, which is B3HT. It's one of the polymer that is used for transistors and also for solar cells. So I initially just watched at this material. So we started by two different states in solution. One of them is pre-aggregated, and one of them is well dissolved. And we have obtained this by using a marginal solvent. So this marginal solvent, it can affect the aggregation of B3HT. So if we store it for days in without stirring, then we can have some pre-aggregation. But if we heat it and continue stirring the solution, we can get a well-dissolved state. And as we can see here at the beginning of a spin coating, we can see here these peaks of from the absorption. They are vibronic peaks, and this related to the aggregation of B3HT in solution. And we can see these clearly in the initial state. And during spin coating, we can see differences into the dynamics. We can have a larger time for the formation with the pre-aggregated solution, and this results in a large effect on the final state. We can see here the formation of fibrils for the one with pre-aggregated, but we don't have fibrils in the well-dissolved one. And also we can see we have a higher crystallinity. And if we make transistors from these, we get very high mobility for the one with pre-aggregated. I think because of these fibrils, it's highly crystalline, and they can improve the electron and hole movement during the film. So with the pre-aggregation of the solution, we can get a much better product at the end. So we applied the same thing into solar cells. We tried to use B3HT. We blended it with another material, which is acceptor. So B3HT is used here as a donor. So we tried also to see the process, spin coating process. We have tried to change the processing conditions. And what we observe here, we have differences also in the formation dynamics. So we have much longer time for the black curve here, which also has implication on the final state. We can see also the black curve here, it has high vibronics. This is indication of high crystallinity of the film and high aggregation in the final film. And we can see also the morphology by TM and FM. So we can see for the case with the longer dynamics, we can see here larger domains of the donor acceptor materials, and this is improved phase separation. So this material can have a better performance. As we have tested the devices, we can get a much higher performance for the one that was used with 900 RPM and 45 seconds. And this also we could link between the dynamics of film formation and the final product, and we could understand why this happens. And this was mainly due to the increase in the dynamics of the aggregation. So the material itself has longer time to self-assemble and crystallize. So it improves the crystallinity in the final film, and this helps also the donor material, acceptor material, to phase separate into more pure domains. So the take-home message from this, so we have implemented a new technique that was for the first time to get time resolved UV absorption during the spin coating, and we have applied this into two different categories of application. One in the thin film transistor for a single component, the B3HT material, and also for solar cells. And what we have found, if we have a large difference in the aggregation state in the solution, we can affect the formation dynamics and the aggregation dynamics of the polymer, and this will affect the final product. And also for the solar cells, we have found if we change the dynamics, we can tune the final microstructure, and we can tune the crystallization in the final film, and this also has implication on the solar cell performance. So now we move to a different topic. So the previous topic we were investigating, we are applying a new technique into different processing conditions. But for this one, we will try to understand the design of the molecule, how it is affecting the self-assembly of the molecule, and how it is affecting the film formation. So for this one, we use small molecules as a donor material, and we use BCBM as an acceptor material. So we started by a material called T1, which is a small molecule, and we tried to vary the backbone of the material. We changed the units here and tried to understand how the effect of this molecular design into the film formation and into the final product. So we tried to use different in situ techniques. We used in situ absorption and also in situ X-ray diffraction. And also we combined this with flash DC, which we we try to crystallize the material from the melt very quickly and try to see what's happening. So when we started initially with the material T1, what we have found for T1, so when we just cast them normally, we found that it's getting trapped into a liquid crystalline weakly ordered case. And with time, this phase, which is weakly ordered and it's very low crystallinity, it evolves over days into a highly crystalline phase. But so we tried to use some additives in order to induce this in order to induce this in a shorter time, because we can't wait for days in order to process the material. So we use some sort of additives that can dissolve the liquid crystalline phase, which we don't want in the final product to form the final product. So the additives, we found that it can dissolve the liquid crystalline phase and it can help to form the highly crystalline phase during seconds or tens of seconds if we have blends. So when we blend it with acceptor, it takes a slightly longer time in order to transform from the liquid crystalline phase into the final phase. And we try to link this also with the crystallization from melt. And we have found this material, if we melt it very fast, also we can quench it into a liquid crystalline phase. So this material, it has a problem in the self-assembly. When it tries to self-assemble, it has intermediate metastable phase, and this phase is weakly ordered and has low absorption and has low conductivity. So it is not appropriate for the final product. But we need to use some additives in order to transform this unwanted phase into a wanted phase. So as we can see here, if we process a material without additives, here on the left, we get a liquid crystalline phase, and also in here the red color and blue color, they are for the donor acceptor material. We don't get a good phase separation, and we can see here as we process the material, as we looked at in situ, we can see here without additives, the material is trapped into liquid crystalline phase, but with additives we can dissociate the liquid crystalline phase and form the crystalline phase. And if we process with additives here on the right, we can see we can form the highly crystalline phase during spin coating. And also we can see here we have larger phase separation. So the one on the left, it has very poor phase separation. The donor acceptor material are mixed. So this material cannot extract the charges efficiently. But the one on the right, because we have sufficient phase separation, we can extract the charges. We get more than 3 times increase in efficiency, as we can see here from the device's performance. So we applied this into T1, and then we applied similar studies into H1 and X2. But I will just go directly into the final conclusion. I will not go in detail into each one. So what we have done with this, we tried to quench them from melt. This is by flash DSC. So we found H1, it's even can be vitrified, it can be quenched easier than T1. But X2, which is another derivative, it cannot be vitrified up to 5,000 Kelvin per second. So the material X2, it can be crystallized much easier. So we can see on the left here, the ease of crystallization is changing from H1 to T1 to X2. And when we try to make a film from this for H1, because it can be vitrified very easily, it forms amorphous compound without additives. But for the second one, it forms weakly ordered liquid crystalline phase, and for the third one, it forms crystalline phase without additives. And if we use additives, we can form crystalline phase for all of them. But for the first 2 materials, we need the additives in order to get high efficiency. But the third one, we don't need the additives. So we linked this by the performance, and we have concluded this with a change of these molecular designs. The need of additives, we linked it to the ease of crystallization. As we improve the ease of crystallization of the molecule, we don't need the additive to process the materials. We can use additive free. And these additives are usually toxic materials. So the additive free is better than with additives, because they can help us to process the material with more green solvents. So the last one, I think, from environmental perspective, it's better than the first 2 because it doesn't require any additives, and it can be done in just 1 step without adding anything to the solution. And we can see here for this X2 material, we can get a very high performance because of the ease of crystallization, and we can get phase separation very easily without any additives. And the take-home messages from this, so we can find that we could link the ease of crystallization to the need of a specific processing technique, and we have applied this by understanding the in situ film formation. We try to watch the materials as it happens, and we could see the intermediate phases that they form, and we could link this to the final product and final application. And also we have found that for the material H1 and T1, because they can be vitrified into metastable phases, they need some solvent additives in order to transform them into a more crystalline phase. And for the materials that doesn't require any uh, any uh, any additives, these are materials that can crystallize much easier. So the materials that can self-assemble and crystallize in solution without any help, they can be processed without any additives. So we try to apply this into larger scale areas. So we try to compare spin coating here on the left with wire bar coating. So spin coating, it's a technique that wastes a lot of material. We add solutions, and when we spin the substrate, more than 90% of the solution is wasted. So this kind of a waste of material, it's difficult to apply it in industry. But if we use some other techniques like wire bar coating, blade coating, slot die coating, all of these techniques can be applied into large area. So we try to use this with T1 as well. And we used BCBM as acceptor. So the initial trials that when we do spin coating, we have a uniform film. If we do bar coating, we found the film is non-uniform. We found the formation of very large crystals. And this also leads to the formation of pinholes. So in order to overcome this, we investigated the spin coating and bar coating in situ, and we found the problem comes from the wire bar coating itself. It was inducing larger scale phase separation, and also was inducing over crystallization because the T1 material was crystallizing in solution at room. If we do the blade coating, if we do the wire bar coating at room temperature, and if we increase the temperature, we also get the same problem with very high large domains of the T1 material. So we have invented a new technique. It's a modified bar coating, and we have patented this. So we tried to modify the drying of the material in order to overcome this problem, in order to overcome the overcrystallization. And we could successfully, with this technique, we could successfully get the same crystallinity, the same domain size of T1 materials, and also the same average crystal size and the same crystallinity. And also when we apply it to devices, we could get similar performance. It's even slightly better for the modified bar coating as compared to the spin coating. And to prove that this is scalable, we have done the processing in air. So usually these are done in glove box, which has a slightly higher performance because one of the layers that is used, it's reactive with the moisture. So it has high performance in glove box, but in order to prove that this is scalable, we have done all experiments in air, and we could get a relatively high performance for the modified bar coating. And so this we could reach this by only watching what's happening in situ and understanding what are the challenges, and then trying to solve the problem. And the solution was not to use the wire bar coating that's available in the market, but we needed to modify it to a new apparatus that can help us to get the final product in the appropriate way. And the take-home message from this: so if we try to understand the microstructure development during film formation by the in situ characterization techniques, we can have a better understanding, and we can also apply this into larger scale production. And the modified bar coating that we have invented, it helped us to get a good film with good microstructure and good solar cell performance. So then now I will move to the different class of material, but I think maybe I will just give a minute of a brief 1 minute just to, for relaxing, and then I will continue.
Ladies and gentlemen, if you have a question, you may raise your hand there in participant, or you may send the question in Q&A chat, please.
So in the second topic, I think should I continue now? Okay.
Yeah, you have 10 more minutes, huh?
Yeah.
10 to 15
Okay, sure.
minutes.
So in the second topic, so I will give some thoughts about hybrid organic inorganic perovskite materials. I will give a brief introduction into this class of material, and then I will try to discuss some of the findings related to this material. So for the perovskite material, it's completely different class, and the solar cells, it's working with a slightly different mechanism. So for this material, we have a low binding energy. So for organics, we said that we have a high binding energy. It means the electrons and holes are bound together, and it's difficult to separate them into free electron and holes. But for this material, it has a very low binding energy. Just at room temperature, the thermal energy at room temperature is sufficient to form electrons and holes, free charges. So without the need of having a donor material and acceptor material and interface. So it makes it much more simpler because we can just have a layer of the active material, which is a perovskite material, and we can have a whole transporting an electron transport material and electrodes. So it doesn't require the complexity of a bulk heterojunction. It can be just processed in one layer. And this material also, it has a lot of advantages. It has high tunability over parts. So the crystal structure here, it's a perovskite structure. It's named after a Russian scientist called Perovskite, and he discovered this class of structures, and it can be different materials. But I'm focusing here mainly on the lead halide materials. In the A side, we can have different materials. We can have cesium, we can have methyl ammonium, we can have formamidinium. So these materials can be also mixed. We can have cesium Ma, cesium Fa, and we use lead in the B side, and also we have a halide material in the X side. So with the change of the structure, we can have completely different properties. We can tune the absorption, we can tune the conductivity, we can tune everything based on the choice of these materials. And also it has a low electron hole binding energy. Most of these materials, just at room temperature, we can have free electrons and holes after absorption. And also they have a high diffusion length, so we can have a very thick film without the problem of diffusion length. I think for organics also it has a problem with diffusion length. The excipients can move only small distance before combining, but for this one, the diffusion is much longer. It can reach micrometers. So the charges can move micrometers without recombining. So this is also a good thing for this material. But one of the challenges that this material also is more complex in terms of the synthesis. So with organic materials, we synthesize the small molecules of polymers, and then we try to process the film, but we are not changing this during the processing. But for this material, we start by solution. We have isolated ions of different materials that we choose, and we end up with a final product. But on the way, we have a competition of different phases. We can form other phases, which is non-perovskite phases, and these phases, they are not good for the solar cells. And also we can have complexes with the solvent. So we can have the perovskite material itself crystallize in a different structure that is not favorable, or we can form a complexes with the solvents that we are using, and this makes it more complex. So we might start by a specific compound, and then we end up with some intermediate phases, and we can stuck on these intermediate phases unless we modify our processing techniques. So again, here the in situ characterization is very necessary in order to understand the action pathway, how this happens from solution to the final product. And this, we will try to apply this into different topics also that I have studied during my postdocs. So for the first topic here, I'm trying to compare different processing techniques. I try to compare dropping anti-solvent with applying nitrogen. So dropping anti-solvent, so it's kind of a methodology that we use to tune the microstructure. So for spin coating, we start by solution, and then we drop an anti-solvent. This anti-solvent induces some changes in the film, and then we get an ice-cast film, and then we anneal this film for the final product. For the other treatment, we apply some nitrogen jet in order to also change the formation, and then we get ice-cast film, and then this film we anneal it. So I try to watch these changes during film formation in order to understand the mechanism of each of these. So I have applied this. I have chosen cesium Fa. So it's a compound cesium atom, and then Fa, it's an organic molecule. So this is in the A side with lead and iodide. And this compound, it has a competition with other phases like a delta phase of FA and delta phase of cesium, and this can compete with each other during film formation. So we might stuck with some of these intermediate phases, and we need to form the final product. So I try to employ in situ X-ray scattering in order to understand, to get information about the phases that they are formed and the composition, so we could know what is the composition and how it changes over time. And also we could get the film fraction. So the film, it has amorphous phase, it has delta phase and alpha phase, and this it changes in fractional time until we reach the final state. And with in situ techniques, we could track all these changes, and we could understand how these techniques is used to tune the microstructure. So this is kind of the final thoughts that we reached for the dropping antisolvent. So what we understood from the mechanism of this, so when we drop antisolvent, because it's antisolvent, once it's mixing with the solution, it's creating a supersaturation immediately. So we get immediate crystallization from the bulk, and because that antisolvent diffuses into the bulk, we get a randomly oriented crystals in the bulk. But for nitrogen drying, it's working with different completely mechanism. So the nitrogen itself, it's removing volatiles from the top surface, and this leads to a local saturation of the top surface. And this gives us highly oriented crystals, but these crystals are not the final product. They are from the delta phase. And as we increase the nitrogen drying time, then we get supersaturation into the bulk. So we initially have a local supersaturation on the top surface, and then we have saturation in the bulk, and we get some randomly oriented crystals in the bulk. So we have kind of two steps that's happening during this process. And in both cases, after we form the film, we end up with delta phase and alpha phase, and also some amorphous phase. So this is kind of the picture, what's happening during film formation. This is the as-cast film. After we spin coat the film, we get some delta phase and some delta phase and some alpha phase, and also some amorphous materials. But we need to reach to the final product on the right, which is the black phase. And when we tune this, what we've found about the mechanism, so we found that the delta phase dissociate as we apply annealing, and delta phase we found it's mainly pure Fa. But the alpha phase we found it has different composition than the final state. The final state, the cesium has 15%. And Fa 85%. But when we've watched at form formation, we found initially the crystalline phase, the perovskite phase was having different composition, was having 30% cesium. So we have a segregation. So the cesium goes into the alpha phase, and Fa goes into the delta phase. And as we apply annealing, the annealing helps to dissociate the delta phase. And after dissociation, the molecules that are dissociated from the delta phase diffuse and contribute to the growth of the alpha phase. And with time, the Fa dilutes the cesium, and we reach to a uniform film with the final product. So we could reach this understanding by applying in situ characterization to understand what is the mechanism of formation. So we tried also to apply this into blade coating. The previous study was spin coating, and after spin coating, we were doing annealing. So we tried to compare this to a technique that can be applied for scalable fabrication. So again, here we use the blade coating. So the blade coating, it's a technique that can be applied by roll-to-roll processing and can be used like printing papers. We try to understand the competition between these phases at different temperatures. So the blade coating also we can apply heat. We can apply heating to the substrate as the coating happens. So we try to see the competition at different temperatures. What we have found, above 70 degrees, we have found that the alpha phase becomes more dominant than the delta phase, and below 70 degrees, we have the delta phase is more dominant. So when we try to do blade coating at 50 degrees, we end up with a film that has both delta phase and alpha phase, and this is not favorable because we still need a second step of annealing. But if we use blade coating at higher temperatures, we can get rid of the delta phase and we form directly the alpha phase. We found that we see some delta phase that form and disappear very quickly, but at 90 degrees we can get the final product directly without having a second step of annealing. And I think this was very beneficial because here also the temperature of blade coating was 90 degrees, but when we do annealing for after spin coating, we need higher temperatures. So when we do blade coating, we found that we can also use a lower temperature in order to process the film, and we can do only one step without doing spin coating and then annealing. We can just do one blade coating, and in a few seconds we form the final product directly if we have sufficiently high temperature. And the take-home message from this, we found that two treatments that we apply chlorobenzene treatment or the nitrogen drying treatment. Both of them, they work with different mechanisms, but we end up with a phase segregated domain in which we have more of the cesium goes into the alpha phase and the FA goes to the delta phase. Healing is needed for both cases, in which the thermal annealing helps to form a homogeneous film where it helps to dissociate the delta phase and diffusion of the delta phase compounds into the alpha phase and form a uniform film with cesium and Fa with appropriate stoichiometry. For the spin coating techniques at room temperature, we usually end up with a film that has amorphous and delta phase and alpha phase, which requires heating. But if we use blade coating, alternatively, we can form a perovskite in one step. So we move now to the final topic, which we apply room temperature processing. And the main benefits from room temperature processing is also related to scalability. So if we use a room temperature processing, it can help us to scale up the process much easier than if we use annealing. And with this, we use some additives. We use some additives in order to tune microstructure and also in order to help this process to happen at room temperature without the need for thermal annealing at all. And as we can see here, we have methyl ammonium thiocyanate. It's a salt material that we add into the precrystal solution. And we have found if we don't use this, we end up with a film that has small grains of the crystals surrounded by unconverted material. So the dark colors here, it's just material that is not converted. So we need thermal annealing in order to form the perovskite phase. But if we use the additives, we found we can form very large crystals, micron-sized crystals of perovskite at room temperature without the need of the thermal annealing. But here also we need to dry the film. We can use nitrogen drying to dry the film, or we can use low vacuum to dry the film. And we try to employ in situ characterization techniques. We applied in situ X-ray, and also we applied in situ BL. And the reason here for using in situ BL, the photoluminescence is more sensitive to very small nanocrystals. But the X-ray, it needs slightly larger crystals in order to see some diffraction. So the BL can detect the nanocrystals as they form, so it can detect the nucleation and growth. So what we have applied for this material, so without additives on the left and with additive on the right. So what we have seen the aggregation presence of additives. If you use additives, we have very large aggregates in solution. And this also affects the process as during spin coating. We found during spin coating, if we don't have additives, we form a very confined crystals. And we know this from the confinement of the BL emission. So the BL at higher energy, it means we have quantum confinement, which is related to formation of much smaller crystals. But if we have additives, we have a slightly larger crystals at the beginning that grows very quickly into much larger crystals. And this is here the BL. It's related to the large crystal at the end of the spin coating. And we could correlate the aggregate size in solution with the final average crystal size. We have found as we have larger aggregate solution, we get a larger crystal sizes in the final film. We can get crystal sizes in the order of microns if we use additives. And for here I'm summarizing the mechanism. So what we have found, if we don't use additives, we get very small aggregates in solution, and this leads to high nucleation density of metastable phase, which is the blue material here. It's a complex between the perovskite material and the solvent. So this one is unwanted, and the material is trapped in this. If we do nitrogen drying, this material is relatively stable at room temperature, so it doesn't decompose. So we get very small domains of the perovskite crystals, which is here marked as black, and we have a lot of material that is left with the blue material, which is intermediate complex that we need to remove. And we cannot remove this at room temperature. We have to heat the film and anneal it in order to get rid of the intermediate phase. But if we use additives, what we have found, we have large aggregates in solution, and these large aggregates leads to larger crystals in the as-cast film, as we can see here, and also this leads to lower nucleation density. And as we apply nitrogen drying, we remove the volatiles from the top surface, and this leads to MACN, which is the additives, to diffuse within the film. And this, as it is diffusing within the film, it's reacting with the intermediate phases, and it's dissociating these intermediate phases and helps to grow the crystals. So during the nitrogen drying, we have found that the MACN, it's interacting with the intermediate phases, and we found here two different intermediate phases. One is unknown, and one is an intermediate phase with DMSO, which is one of the solvent that we use. And for both cases, for both intermediates, we have found that MACN can dissociate both of them very quickly at room temperature, and this, after dissociation, they contribute to the growth of the perovskite phase. And this happens at room temperature and leads to formation of very large crystals. And from this also, we could understand the reaction battery. So this is a blue material. It has this composition. So this material, it reacts with the amorphous material surrounding it, which has different components. It has MI, and this reaction happens, and then we form the final product, which is the perovskite materials. And the additive here helps to dissociate this. So this reaction, it can go both sides. So the perovskite can dissociate into the intermediate as well as the presence of solvent. But if we have the additives, we have found the additive, it destabilizes this compound. It reacts with this compound and makes it unstable. So this dissociates, and after dissociation, these molecules diffuse, and also it's joins some amorphous material, and both of them contribute to the growth of the crystalline phase. And the DMSO, it's a solvent, so it goes to amorphous material, and from the amorphous material, it goes to outside the film. So it evaporates eventually with the drying. And the presence of additives here was very important, as it helps to dissociate the intermediate phases and form the final crystalline phase. As the take composition found about the role of the additive. So in solution, it induces large aggregates, and during spin coating, because we have large aggregates, it tends to form larger crystals, and these larger crystals has lower nucleation density. And if we apply nitrogen, so the additive helps to dissociate and decompose the intermediate phases and helps to grow the perovskite phase. And if we don't have additives, so the perovskite formation and dissociation doesn't happen efficiently at room temperature, because some of these intermediate phases are very stable at room temperature, so we need thermal annealing for these. And now I move to the final part, which is the current and future directions. So currently I'm trying to apply this into also different classes of materials like oxides and halides, and I'm using also perovskite materials. What I'm trying also to do is so some of these research that I have done before, I was doing partial automation, which means when I do in CQ X-ray, I need to. This experiment is done in a closed room that we cannot have access to it. So I need to control the synthesis remotely. So usually I do automation of the synthesis. So, but I was doing this partially. So currently I'm trying to have larger automation of the process by controlling the synthesis and doing some automation of this. And also I'm trying to do with collaboration with other groups in Berkeley, we are trying to apply machine learning. So we apply machine learning tools into the literature to get the processing structure property relationships from literature, and try to create a machine learning model, and using this model to test it if the model is appropriate, and use this to guide the synthesis. So we can get from the literature some information that can help us to provide us guidelines how to control the microstructure. And if this model is not successful, we need to reconstruct the model again in order to get a more comprehensive model that can help us to control the synthesis process. And also, I'm trying also to combine the automation with machine learning, and the combining means we apply the machine learning into the automation of the process. So we automate the synthesis itself, and we apply machine learning to learn from the automated characterization, and use this to tune directly the material synthesis during the synthesis itself. So for this one is different than from literature, is from the experiment itself, and try to tune it as it happens. And I would like to acknowledge my advisors and also my collaborators, and thanks for everyone.
Okay, thank you very much, Dr. Abdelsamie. It was excellent talk, and I'm sure there are a few questions here. So I will take the first question, and question will be, you may have the follow-up question if anybody asking. If no more question, then we may continue. So first question is from Dr. Janjua. You may unmute Dr. Janjua yourself.
Yes, thank you. Thank you very much. May I ask, sir?
Yes, please go ahead.
Yes, Dr. Majid Abdelsamie, very nice presentation and excellent, very interesting. Actually, I'm working with the density function theory calculations of such molecules, including organic solar cells, non-linear optical materials, functional materials, even this one, perovskites. So I have just, after watching your excellent presentation, I have just I'm curious about that, because as a computational chemist, I don't know about those things. For example, recently, I have performed calculations on, triphenylamine based, you can say, transport whole materials. And where definitely, I also calculated the interaction between that TPA and PCBM. So I'm curious about, based on this, I'm just curious that how do you remove this perovskite film from certain areas on the substrate, and same, how can you remove that PCBM layer? This is my first question. And the second question.
Remove what? Can you say again? How can you remove?
Yes, how can you remove that perovskite film from certain areas on the substrate? I mean, from position of the cathode, how can you do that? Because as a computational chemist, I don't know. I do everything in gas phase, so I can model anything if I know the information. And same is the case that how do you remove the PCBM layer?
Why do you want to remove the PCM layer?
I mean, when you are going to in real time, when you are going to make one film, how you are going to keep that, and how you are going to keeping in some solvent which is before converting into a film. So this is just I'm curious about that.
Okay, so you mix the materials in solution. So you have the polymer material and the PCBM material, or the small molecule and PCBM material in solution, and as you remove the solvent, you don't remove the PCBM. So when you spin coat the film, so you remove the solvent, and as you remove the solvent, the PCBM itself starts to aggregate, and also the polymer or small molecule starts to aggregate, and then form domains. These domains can be in nanoscale or can be in very large scales. So you can tune this by changing the processing conditions. You can add some additives that can make the domains larger or smaller. So, but you don't remove PCBM, you remove the solvent, and the solvent it's a volatile material, so it will be removed by itself. It will evaporate. So the material itself it tends to evaporate, and what we do, it's by spin coating. You remove it because in a spin coating, as you rotate the material, it interacts with the air on top of it. So when you spin the material very fast, so you have some air layer on top of the spinning material, and this air layer it tends to remove the volatile. So you have kind of a pressure, and this the spinning itself, it helps to remove the solvent from the film. But if it's not removed during spin coating, then you apply some heating or annealing. Some of the solvents require high temperature, like depends on what you use. If you use, for example, chloroform, at room temperature will be evaporated. If you use, for example, DIO, it will not evaporate. It will take hours to evaporate. So sometimes you need to heat it at 60 degrees or 70 degrees to dry. So you remove the solvent. Usually, most of solvents would be removed during spin coating, but if it's not removed because you use a very high boiling point solvent, then you need to use temperature, or also you can use a vacuum. For some of these, if you put them in a vacuum chamber for a short time, you can remove the solvents.
Okay.
Thank you very much, Dr. Abdelsamie. Let's go to the next question. Amal, you can unmute yourself.
Yeah, thank you so much. Hi, Dr. Abdelsamie. I have 3 questions. First one, when you prepare and when you synthesize 2 phases, and slide 32, I think.
32?
You say, yeah, 32. You find 2 phases. My question here, there is any difference in the absorbance spectra between these phases, or they are the same?
Yeah, of course, they have large differences. So the perovskite material, it's high absorbing. It has it can absorb a lot of light. For the other material, it's yellow material. So as I have it here, the black material, it's black because it's absorbing almost all the light.
So
the other material is yellow, so it's absorbing only the yellow part. Yeah.
Okay. My question here also, when you use the two techniques, my question here, there is an effect for these two methods in the transport properties and diffusion properties, or the two techniques, they have the same properties?
So these techniques, they have different mechanisms.
I mean, when you add the solvent, is the solvent affect transport properties and diffusion properties?
Yeah, of course. The choice of solvent also is one way to control the whole thing. So here I'm using DMF and DMSO. So both of them are, if we use only DMF only or DMSO only, it doesn't work well. And I think the reason for that.
What do you mean by it doesn't work?
So the film quality is bad. So what we end up with, we end up with rough film, and the rough film can also have some pinholes. So if you use dual solvent, I think the dual solvent itself is better, and I think it's also related to the intermediates. So the DMF itself, when it forms intermediates, it forms very large fibrils of the intermediate, and this is kind of intermediate that gives lower quality of the film at the end after thermal annealing. But with DMSO, it forms the intermediate itself. It doesn't have this large fibril structures. So the DMSO itself, it's forming a more uniform film that also gives like a much smoother film. So that choice of solvent, it has a large effect in the final product. So I think the community was using initial DMF, but they found it's not giving the appropriate properties. So they tried to add some DMSO into it. Yeah.
Thank you very much, Amal. You can hold the third question. We have to move only for one and two questions. Okay.
No problem.
Dr. Almaz.
Thank you so much. Thank you.
Okay,
thank you.
Dr. Almaz.
Thank you very much, Dr. Majid, for excellent talk, very informative talk. I have a couple of questions, all of them related to the organic.
Not more than two, Almaz.
Okay, two questions. Both of them related to organic solar cells. And in the organic solar cells, your solar cell efficiency values are quite low, and it's increased quite marginally from 3%, 4%, 5% in some examples. I was just wondering how accurate these values. Do you have the error bars? Because I haven't seen the error bars in the tables you have shown. And then the other question is quite general, related to organic solar cells, and the efficiency is relatively low compared to the silicon or perovskites, where perovskite silicons are around 20% or more the solar cell efficiencies. I'm just wondering, what is the future of this field, organic solar cells? Is it really promising? And if there is any important research fields that you can address, what are those research fields that you can address to basically maybe improve that, to go to at least to the level of the perovskite solar cells? And then the other small question is related to this absorbance at the crystalline phases. You said that these vibronic structures are related to the crystalline structures. How can you elaborate more how this correlation works? How vibronic structure gives you more information about the crystallity of the structure? Thank you very much.
Okay. So for the first question, for the efficiency, so the efficiencies that I'm proposing now, so the first one is BCH-TB. It's a standard material that is used, so it's not used for high efficient, but it's a standard material. So most of the techniques, when you apply, we will try to apply to BCH-TB, and this was back in 2013 and 14. So it's low efficiency material, but it's still used as a model system because it's well studied. But there are other high efficiency materials. So also for the small molecules that I have done, so the efficiency that was giving 7.6%, this was a record efficiency at the time for the small molecules processed without an additives. And the highest efficiency was for polymer, which was but it was polymer processed with additives. but it was 10% at this time. But now the efficiency has increased to 15%. So I think I was doing this during my PhD. So now, after 5 years, from the time that I have done these experiments, the efficiency has increased from 8 to 10% to now 15, 16%. So the efficiency now of organics has reached 15 to 16%. So it's now competing with perovskite. But still, perovskite has much higher efficiency. But there are also other drawbacks for perovskite. It uses lead, so the lead is toxic material. And also the lead itself, it's more sensitive to moisture. So if you have moisture, the perovskite material might dissolve in this moisture. So it might be more, in terms of safety, it's less favorable. But for organics, they are more abundant materials. They are more safe also to use, and the efficiency is still increasing. So now I think the community in OPV, they invented the ternary devices and quaternary devices that has much higher efficiencies. And also they moved away from fluorines into other non-fluorine acceptors, which also has given higher efficiencies. But I think the reason that I didn't do more of OPV during my postdocs, that I was trying to understand new fields. So if I continue doing only OPV all my life, I will not learn new things. So that's why I moved away from the field. But still, the field is evolving and people are increasing the efficiency, although I'm not working in that directly now. But in the future, I can still work in the field itself. Yeah, well, the second question was what the vibronic peaks. Okay, so the vibronics is related to the how the planar of the backbone of the polymer and how they interact with the other one. So if when you have just isolated molecules, you don't have vibronic peaks, you just have the amorphous. But when they are interacting with each other, like you have intermolecular interactions, or also you have a more rigid backbone by having ordered, then you start to form the vibronic peaks. It's evolving from this interaction as the by starts to evolve, then you start to get this vibronic peaks. But it's not conclusive that it's from crystalline phase, but it's mainly from aggregated phase, which is like semi-crystalline or weakly crystalline. But to get the crystallinity directly, you need to do X-ray diffractions. But it's indirectly related to crystallinity.
Okay, thank you, Dr. Majid. The third question you can hold on. And the next is Dr. Uthman.
Yes, thank you very much, Dr. Nahad. Thank you, Doctor, for a nice presentation. I have two questions. The first one is, did you study the stability of your perovskites? This is number one. And under different conditions, let us say under summer conditions or winter conditions. And the second question is, how did you try to stabilize lead in your perovskites from leaking from your cells? Did you use any certain type of encapsulation in these materials or not? Thank you.
Okay, thank you. So I haven't done this by myself because my work is mainly related to the film formation of the active layer itself. So I haven't done this by myself, but a lot of groups, they have done these experiments. For example, when the dropping anti-solvent and applying nitrogen drying. So these methodologies was published earlier before I do my work by NREL. So they have investigated these techniques and they have investigated the stability of the cesium Fa. So they have found when you use a mixed cations like cesium Fa or adding Ma, you get more stability. And they have found just for cesium Fa, it was stable for a month and was decaying after this. After this into the compound cesium Fa Ma. So they have like three cations. Then they have extended this stability for longer. So I didn't do the stability measurement by myself, but these compounds that I investigated, the stability of these were investigated by different groups, including NREL, which they were our collaborators. So we're working in different projects. So they have studied stability. We have studied the film formation. And the stability of this, if this can range from months to 2 years based on the choice of the material. So this kind of for stability. So it can be stabilized as we mix the compounds. If you just use the pure compound like pure cesium or pure Fa, pure Ma, the materials are not stable at all. But when you try to mix it cations or mix it anions, then you can improve the stability.
Okay, and
yeah.
Yes, continue, please.
Yeah, for the second questions about how do you prevent the lead from leaving the film. So I think people use some layers in order to prevent this. So you coat another layer on top of the active layer of the perovskite that that has dual passivation of the active layer. So people have done this, and so I think there is a different class of material which is 2D perovskite. It has more stability. So some people they have the 3D perovskite, which is the active layer that I was explaining now, and they apply to it 2D perovskite material on the top that extends the stability significantly. And one of the groups that has done this was Naziruddin. So he has done this. He has done this with blue materials. He could get very long stability when he applies different layers. So he applies a passivation layer on top of the perovskite to prevent it from dissolving.
Okay, thank you very much.
Just final question, Dr. Muhammad.
Just please wait. Everybody was, allowed 2 questions. So third one, if you are in the line, we will see. Next is Dr. Fahad Suleiman. You can unmute yourself.
Assalamu alaikum. First of all, I would like to thank you for this excellent presentation and the update about this important technology. My question overall relevant to organic-based or polymer-based PV system. What do you think about, first of all, the upper theoretical limit of the efficiency and stability of this one in the future, either pure organic PV or hybrid system? So what do you think about the future of this one and to compete with other types like silicon-based or thin films?
Yeah, so I think for this materials, the community also realized that they cannot compete silicon, they cannot replace silicon. So the community now is trying to use this as tandems with silicon, or to propose them in a fields that requires, like, for example, low lifetime. For example, so silicon solar cells, they can live for 20 years or more. So I think either class of materials, either perovskites or organics, they cannot compete silicon in this. But the silicon itself it's because it can have 20 years and also can have very large area. So it's more like you create a large factory of silicon solar cells that stays for a longer time. But the organic or perovskites can be used in other applications. Like you can have them in the windows. You can have them in the lightweight stuff, like you can have them on the bags. So they can be used in alternative in other places that you cannot have silicon, like you cannot carry a bag with a silicon solar cells on it. Or also for some projects that are done not permanently, like you have a project that will be done, for example, in a desert for 2 years. So instead of buying a very, very expensive solar cell that will live for example 20 years, you can have a cheaper one that can have just the application for you for the short period. So they can be used in different applications. They cannot compete. They are not competing with each other. They're trying to use the organics or perovskites as like as a supporting, or as like it's alternative in fields that silicon cannot apply. And in terms of efficiency, I think their limit will not reach to the highest efficiency of silicon solar cells. So theoretically, some of them, if they use it in tandems, they can reach to 30% to 40%. But I think with the current status, it's difficult to even reach 30%. So it's gonna be very difficult to compete with silicon. So the community now is just trying to apply it in different fields that silicon cannot be applied to, or to use it with tandem. Like some people also try to have a perovskite solar cell on top of the silicon as a tandem to improve the efficiency of the silicon. And in this case, you will use a transparent layer of silicon. Also, some people try to use tandem of organic on top of the silicon. Yeah, so I don't think it will compete silicon, but it can be used in different applications.
Thank you. So if it is used as a tandem, OPV with silicon, for what reason and what will be the improvement in the performance?
So I think you when you use a tandem, you use a transparent rail, so you can still extend. I think it depends on what kind of tandem you use. You might improve for example, the voltage. If you use tandem, so you have higher voltage. You can also improve the efficiency if you use, for example, perovskites. You have a thin layer of the perovskite. When you use tandem, you can have a higher efficiency. I think Mike McGee group has done theoretical calculations of these, and also he has applied this into application, and he could found that if you have tandem of material, you can still have efficiency, but you need to have a thin layer You cannot use it in full potential. So you need to have it as transparent because the light has to transmit through it in order to go to the silicon. So still with theoretical calculations, you can have improved efficiency. And some people, they have applied this and they could improve efficiency by tandems.
Thank you.
It is done. Thank you very much. And before closing, I would like to just give you, last question. If it is a short answer, Dr. Amal, you want to ask the last question, and then I will close it here.
Thank you so much. My question, curious question. So because I'm a chemist and I'm interested in the synthesized material, and as the presenter also mentioned, he will applying a new method for the synthesis. My question here, to go far away from lead, PP, can we replace lead with bismuth? Because bismuth almost has the crystal structure and electronic structure as lead. So I'm curious, it's possible to apply bismuth instead of lead or not?
Also, bismuth cannot replace lead because of the charge. The charge itself, bismuth is 3. So and lead in this structure is 2. So you cannot just use bismuth, but you can use a bismuth with another compound. You can have like a double perovskite. So like, for example, you can use silver bismuth. So silver bismuth, it will have the same charge as lead. So some people, they have done this, they use double perovskite. So they replaced lead with 2 compounds, not just bismuth, like silver bismuth. So then you have the neutral charge. But I think people, they applied this, but they couldn't get the same efficiency. So there's still research now that is done in replacing the lead with other materials, and including bismuth. Bismuth is used, but with other material because of the charge difference between bismuth and lead. But its efficiency is much lower. And these materials also was found it's in direct band gap, so they don't absorb light well. So they have very wide band gap, and their absorption is much lower than the lead perovskites. And their efficiency was from 2 to 5%, so was much lower. But there is still research on this area.
Okay,
thank you so much.
Okay, thank you very much. Thank you, Dr. Abdelsamie. It's we are getting late, and on behalf of the chemistry department, I want to thank you. If Dr. Khalid Hushani is present, would like to say a few words, or should I close? Dr. Khalid Hushani, are you around?
Yes, I would like to thank everybody for, first of all, thank Dr. Majid for his excellent presentation. And thanks everybody for joining us in this wonderful seminar. Thank you, Dr. Nahad, for your effort.
Thank you very much. Assalamu alaikum.
Thank you, everyone.